In this video, we're going to be taking some notes on graphing rational functions. In order to do that, we're going to start back and we're going to remember our graph of our parent function, our inverse variation function of y equals 1 over x, or f of x equals 1 over x. Remember, this thing had a vertical asymptote at x equals 0, so I'm going to write that one down because I wasn't allowed to divide by 0. It had a horizontal asymptote at y equals 0 because I never touched that x-axis. And then when I graphed it, there were only two really nice points on the graph, on the diagonals there. I could graph it using my calculator. I could graph it by making a table. I'll also put it up here on my calculator, 1 over x. And you can see it's just those two branches, and it was called a hyperbola. So then we went back to what we did next, which is we transformed it. And here's an example of g of x. So we're going to take our parent function, and we're going to put a minus 2 on the inside and a plus 3 on the outside, and that's going to give me a new function. It's going to give me this function. So what's that going to do? Well, the minus 2 on the inside is going to move us 2 to the right, and now our vertical asymptote is going to be x equals 2. Let me scroll up a little here. So that's going to make me over 2 to the right for my vertical asymptote. My horizontal asymptote has been bumped up 3, so now it's going to be at y equals 3. And I can also graph that asymptote. And my other points are all going to stay the same. These figures are congruent. They're the same shape. And it looks like this now. So that's the graph transformed. We've written them this way, and we've thought of them like transformations, but we can also rewrite g of x as a single fraction by getting a least common denominator. That's what we just learned how to do. So if I start, my first function was 1 over x minus 2, and then I had a plus 3. If I want to add these two fractions together, I'm going to think of this as 3 over 1. Well, in order to put that with the x minus 2 fraction, I need an x minus 2 on both the top, x minus 2, and the bottom of this fraction. So I'm going to multiply it to the top and bottom. Now on the top, I'll have 1 from my first fraction, plus I'll distribute this 3 to get 3x minus 6. And on the bottom, I'll have x minus 2, which I usually rewrite in a prettier form of 3x minus 5 over x minus 2. So I'm going to scroll down a little more so we can read what's on the bottom of the page here. And what it says when we write it this way, it says when we write the equation this way, we consider it a rational function. A rational function is defined as a function that is the ratio or a fraction of two polynomials. Those were the nice, like a quadratic or a linear like we have, such that the degree of q of x is at least 1. The degree, remember, is the exponent. So on the bottom, we have to have at least an x in order to make it a rational function. And that's what we have here. Our function would be 3x minus 5, which is a linear function. It would make a line if we graphed it, over x minus 2, which is a linear function. It would make a line if we graphed it. And this is another way of writing our function g of x. So when we write it the way we had written it in the beginning of the problem, we can tell it's a transformation. We've moved to the right and we moved up. When we write it this way, we consider it a rational function. And what we're going to do right now is we are going to look at the function presented this way to do a full analysis of their graph. So what I just did is I typed this equation into the y1 in my calculator, and I just want to show you that if I draw it, this looks like the graph I have up there. Remember, my calculator does not do the best job necessarily at showing that what I have here is really an asymptote and what I have here is really an asymptote. We know that that's what the graph looks like, though. So if I turn the page, I've got a lot of words. So these are some of the rules and some of the things that we're going to look at to figure out how we can tell from an equation what's going on with the rational function. For starters, we had the bottom of the function. It starts out and it says division by 0 creates problems in the graph of a rational function. When a denominator equals zeros, two things can happen in the graph. The graph can have either a hole or it can have a vertical asymptote at these values of x. Holes are plotted on the graph as open circles. So they're just going to look like little points, little circles with nothing inside. Asymptotes are plotted as dashed lines. So an asymptote, we've already been doing them, will be plotted as a dashed line. So we've got to figure out in our graph over here on the right, we have a vertical asymptote. Why did we have a vertical asymptote? Because we had division by 0. But not all division by 0 is going to create an asymptote. First thing we have that could happen with division by 0 is a hole. If a factor can be reduced, and that's the key thing right there, if it can be reduced from the top and bottom of a rational function, the graph will have a hole. This is because for that one specific value of x, the function will have division by 0 and will not exist. For any other x values, however, the factor will be insignificant because it would reduce out at the top and bottom. So the x value of a hole is the x value that creates 0 over 0. The y value of the hole is the y value that you get when you plug the x value into the reduced function. So we can also just look at that on our table and just get real close to it. Okay, so that's a hole. The next thing we have happen is a vertical asymptote. So with a vertical asymptote, those were dashed lines, given a rational function, now it's already in reduced form. So we've reduced any common factors from the top and bottom. A vertical asymptote will occur at any value of x that results in division by 0. This is due to the fact that as the denominator gets closer and closer to 0 in value, the y value of the function gets larger and larger. So y would approach either plus or minus infinity. The equation for a vertical asymptote is x equal the number that caused the division by 0. It is the 0 of a factor that cannot be reduced. Okay, so let's turn the page and go over to one of our examples. So if we go to example 3, I've given you an equation here. This is written out sort of in standard form, where all this on the bottom is multiplied out, and that's ugly. I want to look at it in factored form, so I went ahead and gave it to you in factored form as well, so that we can see what happens. So now I've got one factor on the top and 3 factors on the bottom. But you notice I've got this x plus 4 on the top and bottom. That's the same. That factor can be reduced out of the top and bottom. That's what creates a hole, is when I can reduce a factor out of the top and the bottom. The hole is where the x plus 4 factor equals 0. So I would subtract 4 from both sides, and the hole is going to be at x equals negative 4. The other places where we have 0 on the bottom, so at 2x minus 1 equals 0, and at x plus 3 equals 0, those are going to create vertical asymptotes. So I'm going to solve this one by moving the 1 over and dividing by 2. So I have x is a half. I'm going to solve this one by moving the 3 over. So I have x equals 1/2 and x equals negative 3 are both vertical asymptotes. I can have more than one vertical asymptote or more than one hole. If I were to translate these onto my graph, the way I'd do that is at x equals 1/2, I'm going to have a vertical asymptote, and at x equals negative 3, I'm going to have a vertical asymptote. Already I know this can't look like anything I've ever graphed before because I've never had a graph with 2 vertical asymptotes. Now I also had a hole at x equals negative 4. The only problem right now is I don't know where to put it. So right now I'm just going to make a little mark right there. I know I've got to have a hole there because I might miss it when I graph it on my calculator. So let's look back and see what other information we can have. So we're going to go back to our notes page. Inputting large values of x gives the end behavior of a function and determines what happens on the left and right ends of the graph. 2 things can happen in a rational graph. The graph will either level out and be a horizontal asymptote, so it will flatten out on both sides, or it can keep growing and approach plus or minus infinity. So it might shoot off up and down like a line or near the polynomial. The end behavior tells us what is happening on the left and right ends of the graph, not in the middle. So sometimes when we have one of our crazy graphs, it might cross the horizontal asymptote in the middle, or it might cross the slant asymptote. It might go this way. That's okay. We can cross a horizontal or a slant asymptote. So we need to find some equations for these things. To find the equation for a horizontal or slant asymptote, you divide the original equation. Remember, these were all division problems. For really big x's, the remainder is insignificant, so we can just ignore it. The equation of the horizontal asymptote or the slant asymptote is y equals, because it's horizontal, the answer to the division without the remainder. So what we'd like to do is sort of make some shortcuts for how we can figure this out. Here's a little bit of reasoning for you. Horizontal asymptotes, if the degree of the numerator, that's the top, is less than or equal to, so the top's exponent is equal to or smaller than the degree of the denominator, then the graph will have a horizontal asymptote. So this is because when you input large values of x, the y values get closer and closer to a fixed number. The equation of a horizontal asymptote is y equals whatever this number is. So we have the degree of the numerator less than or equal to. So those are two things. If the degree of the numerator and denominator are equal, so if we have something like y equals x cubed over, I got more stuff, x cubed, those would be equal degrees. Then the horizontal asymptote is y equals the ratio of the leading coefficients. So if I had a 4 on top and a 5 on the bottom, then my asymptote right here would be y equals 4/5. Let's flip back to the first page of the notes. You don't have to if you don't want to, but I'll just point. On our function we had down here at the bottom, we had g of x was equal to 3x minus 5 over x minus 2. If I look at the degree of the top and the bottom, they are both x. They are both a degree of 1. So my horizontal asymptote is y equals the ratio of the leading coefficients. So my coefficient at the bottom here would just be a 1. So my horizontal asymptote should be y equals 3 over 1. And if you look back up on the top here, the horizontal asymptote was 3, which is 3 over 1. So that worked there. Okay, let's go back to where we were in the reading. So we also had a second case where the degree of the denominator is bigger. So if we had something like y equals x squared on the top and x cubed on the bottom, we could have other stuff in there too, but the bottom's exponent is bigger. Whenever this happens, the horizontal asymptote is y equals 0. That's going to happen in our example we were doing on the next page. So in this problem, if we look at the degree of the top was 1, the degree of the bottom was 3. So there's more x's on bottom. That means as I plug in really big numbers for x, the bottom is going to get super huge, and a number over a really big number gets smaller and smaller. So our horizontal asymptote is y equals 0. I could also tell this if I look at my graph, and I put this function into my calculator over here. When I typed it in, I have the x plus 4 on the top in parentheses, and then on the bottom of the function, I had to put double parentheses around those factors. I had to put a parenthesis before all of my factors and a second parenthesis after all of my factors. So I can graph this, and you can see it's hard to read off of my calculator, but it does look like it's flattening out in the middle. And this thing is, it's flattening out. Our asymptote is right here at 0. This also corresponds with having my asymptotes at 1/2 and at -3 for my vertical asymptotes like I thought I was going to. So let's put our horizontal asymptote on this graph while we're here. Y equals 0 is our horizontal asymptote, and I'll put that one on there. We do have one more thing that can happen. I mentioned that slant asymptote in our definitions. So let's come back here to our words. And it talks about slant asymptotes. Slant asymptotes, if the degree of the numerator, so the top, is 1 greater than the degree of the denominator. So when the top exponent is bigger than the bottom, so if we have something like y equals x to the 4th over x cubed, then what's going to happen is the graph will have a slant asymptote, where the asymptote is a diagonal line instead of a flat line. We're not going to bother to write the equations for these, but we should recognize that they exist. And again, if we divided, we could find them algebraically. We know how to divide, so we could just divide and ignore the remainder. But I won't ask you to do that. Okay, next up, x and y intercepts. Let's come back to our definitions here. the x and the y-intercepts of a graph tell where the curve hits the axes. You can find x and y-intercepts for rational functions just like you would for any function. So if we have an x and y axis, x-intercepts. For every point on the x-axis has a y value of 0. So if we have an x-intercept, its coordinates are going to be whatever x is, and y is going to be 0. So if we want to find the x-intercepts of a curve, we plug in y equals 0 and figure out what x is. Remember, we have to use the reduced form of the equation because a whole cannot be an intercept. So if we've already canceled a factor out, there's no way that it's going to be an x-intercept. It's gone now. It's just a whole. We can also find the x-intercepts by finding the zeros or the roots on our calculator, or the x-intercepts, whatever button you happen to have on yours. Y-intercepts. The y-intercept is where I touch the y-axis. Every point on the y-axis has an x value of 0. So these points would all be whatever 0 for the x value, and the y value would be 0. So to find the y-intercepts of a curve, I'm going to plug in x equals 0 and solve for y. Again, I have to remember to use the reduced form of the equation because a whole cannot be an intercept. So let's take this and apply it to our problem that we have on the next page. Also, I ask you here for the zeros and the x-intercepts. Remember, those are the same thing. So in the 0 or the x-intercept, I know my y value has to be 0 in there, so I've got to figure out what x is. If I look at my original problem up here, I had my reduced version of the function. So if I'm trying to find the x-intercepts, I'm setting equal to 0 the reduced form. So I would have 1 on top, I would have 2x minus 1 on bottom, and I would have x plus 3 on bottom because the x plus 4 is canceled out. So if I have to solve this equation, well, what am I going to do? I'm going to start out and I'm going to take this and I'm going to multiply it across over to here. When I do that, I multiply it by 0. So I now have left 0 equals 1. Does 0 ever equal 1? No, that never happens. So there's no zeros or no x-intercepts. When you have a horizontal asymptote of 0, oftentimes we don't have x-intercepts. It's not to say we can't, but we don't usually. Okay, to find the y-intercepts, remember for our y-intercept, our x value is 0. So for our y-intercept, I'm going to again go back to the original function in reduced form, and I'm going to plug in 0 for x. So I plugged in 0 for the x in the first factor, 0 for the x in the second factor. If I'm working this out by hand, I now have 2 times 0, which is 0. So then I have a minus 1. And 0 plus 3, which is 3. So I reduce and I get negative 1/3. So my y-intercept is 0, negative 1/3. If I wanted to find this on my calculator, I can go to the G-solve, so I can hit F5. And if I were looking for x-intercepts, I would hit the root button, which is F1, and it would say not found because we didn't have any. If I want to find the y-intercepts, I go to G-solve, I hit F4 for y-intercept, and it tells me negative 0.3 repeating, which is negative 1/3, and that's what I got. So I'm going to scroll down and I'm going to make sure that on my picture down here, I have this y equals negative 1/3. I know it's not a pretty point, but I want to be sure I put it on my graph so I make sure I get close to there. Okay, for the rest of the points to complete my graph, I'm going to have to use my calculator. I can tell, although this looks strange when I look at it in my calculator, it looks like I have something like this is what's graphed on there. Okay, I can't have a graph that looks like that. That looks like an EKG function. One thing that can be helpful on my calculator is I might want to go to the view window, and if I try this F1 INIT, if you have a TI, it's a zoom decimal. Under the zoom menu, you go to decimal. If I do that, sometimes it's a little easier to see where my asymptotes are. And now I get a picture of these were really asymptotes. And my graph really had 3 branches. And when I translate it onto my paper, that's what it needs to look like. To figure out where the points are going to go, I'm going to go into the table menu of my calculator. So I make the table. These points over here, those are just little tiny points. 6.8 times 10 to the negative third, that's almost 0. So all of these points right here are lying close to my x-axis. They're positive, so they're above the x-axis, and the first part of my graph is laying above the x-axis. Now I see I have an error at x equals negative 4. That's because that was a hole, and on my graph I'm going to make a little open circle to show that hole. Then I know I need to shoot up in the air because I could tell that when I looked at the picture. If I wanted to get a more accurate, closer point to the hole, what I could do here is I could type in like a negative 3.9 instead of negative 4, and then I'll get a y value. So I can tell it's still a real small number. X equals negative 3 was an error because that was a vertical asymptote. And I'm going to scroll down and get a few more points here. These points are not very big. They're all really close to the x-axis, but that's okay. I know this thing bent upside down, so I'm just going to plot that on there. Notice I'm not going to cross my asymptotes. I'm going to stay close to them. They're like my fence lines, and I'm going to stay near them, but not actually cross them. Over here on the right of my other vertical asymptote, you notice my vertical asymptote didn't show up, the one at x equals half. If I typed in 0.5 to my table, it would give me an error, but I might miss it if I didn't know that by looking at the factored version. So again, these points right here are all close to the x-axis. I'm shooting up in the air, I'm shooting off to the right, and that's as particular of my graph as I'm going to get. I should be able to answer the rest of the questions on the information sheet, but before I write the domain and range, let's go ahead and look back to the notes part. On the notes, down at the bottom here, it talked about domain and range. It says the domain and range are the possible values of x and y in a function. Division by 0 creates problems, so the domain is always x is not equal to any zeros of the denominator. That included both the holes and the vertical asymptotes. X couldn't be equal to either of those values. For the range, you're going to need to look at the graph. You want to pay close attention to any local maximums or minimums, any holes, and any horizontal asymptotes. Remember, if a y value exists anywhere on the graph, then it's part of the range. So let's look at our graph that we had over here and try and write the domain and range. The domain should be the easier one to write. X such that x is not equal to. What were the three places where the original problem equaled 0? We had negative 4, which was the hole, negative 3, which was a vertical asymptote, and positive 1/2, which was a vertical asymptote. So the domain you should be able to write without looking at a calculator. X can't be 0 on the bottom. To write the range, I have to think about my graph. I want to pay close attention to any horizontal asymptotes, like y equals 0. When I look at my graph, can y ever equal 0? Nope, it can't. Can y be any number above 0? Well, this branch on the right gets very close to the asymptote, and then that branch goes up to forever. I need to watch out for my hole, but it doesn't matter because on the right side of the graph, I covered all those y values. So I'm going to say range, y. Y can be anything greater than 0, or let's look at the other part of the graph. For this part of the graph down here, I look like I can be anything less than 0, but is it really, how high does it go up? I'm not sure. The best way I can tell how high that goes up is to go into my calculator, and I'm going to go back to my graph menu, and I want to hit gsolve max, and that's going to tell me how high it goes up. Well, it doesn't really go all the way up to 0. It only goes up to negative 0.1. So when I write it, I'm going to say y can be less than negative 0.1632 because I go from there down. If I wanted to verify whether or not there was a minimum, I could also on my calculator go to gsolve min, and it says not found, so I know there's no minimum. Okay, let's finish up the rest of this. We had end behavior and increasing, decreasing. So, increasing, decreasing, let me turn off my highlighter here. I'm increasing when from left to right my graph is going up. So all that time I was increasing. I'm increasing because from left to right I'm going up. But then I had a peak, so I stopped increasing. So let's try and describe this part of the graph so far. In this end, I was over at negative infinity because I was on the left. My y value right there was leveling out at 0. I don't care about my y value when I'm increasing and decreasing. I just need the x value. When I'm describing my first interval, I'm going to say I'm increasing from negative infinity, and then where do I stop? I don't exist at the hole, so I have to say I stop at negative 4. Then I start again at negative 4, which is where the hole was, and then I increase until I got to the asymptote, which was at negative 3. Then on the other side of the asymptote, which was still at negative 3, I keep increasing until I get where? Until I get to the x value of my maximum. And where was the x value of my maximum? That was at negative 1.25, which is what I had on my calculator when I found the max. Okay, how about decreasing? A function is decreasing when it falls from left to right. So for this part of the graph, I'm falling, and then on this entire branch, I'm falling again. So how am I going to write that? Well, at negative 1.25, the x value of the maximum, I switch to decreasing. I keep going until I get to my asymptote at a half, and then on the other side at a half, I keep picking up, and then I keep going until forever. This arrow goes to infinity, and the y value goes to 0. But I just want the x value, so I have an infinity. The end behavior we've just taken care of as well, both ends of the graph. So as x goes to negative infinity over here on the left, or as x goes to a positive infinity over here on the right, both sides of the graph are leveling out at 0. This should correspond with your horizontal asymptote, because that's what your horizontal asymptote was telling you, was y equals the value of the end behavior. So that's all the information. I know it is a lot, and we will do a couple more examples on the next page. You can take a look at those and see how these work out for what we've done, but we're definitely going to need to do some practice in class. So here was example 4. In example 4, the problem wasn't given in factored form. So the first thing I did up at the top was to factor it. To look for holes, I want to see if there's any factors that reduce. There aren't any, so there are no holes. The next thing I usually look for are vertical asymptotes. The vertical asymptotes are where the bottom is equal to 0, and where the bottom was equal to 0 was when x equals negative 2 or x equals positive 2. I usually go for the horizontal asymptote next, so I look at the degree of the top and the bottom. In my original equation, I had x on top and x squared on bottom, but when the bottom is bigger, it makes a horizontal asymptote at y equals 0. I would then put this in my graph of my calculator. So when I want to type it in, I need to put x on the top. I'm going to put x in parentheses just because I like to be in the habit of putting everything in parentheses. I also, if I factored it myself, I'm usually going to type it in the original way it was written so that if I made a mistake factoring, I might catch it. I put parentheses around the bottom. I draw this thing and I see it has 3 pieces. Again, I'm in this nice under view window INIT, which was F1. That made me see the pieces I was missing. If I were in a standard window, it looks a little more like an EKG function, so that's why I like that view window INIT a little better. So there's the 3 pieces. That meshes with what I have so far for drawing my asymptotes. As far as finding zeros or X-intercepts, that's where I'm going to plug in y equals 0. If I plug y equals 0 into my original function, the first thing I do is take whatever's on the bottom and multiply it by 0, so it's gone. All that really matters is when does the top equal 0, and that's 0. So 0, 0, I go through the origin. I could also, on my calculator, go to gsolve and hit the root or the y-intercept, and both of those will give me 0, 0. Describing increasing and decreasing. Even though this thing has 3 parts, if I look at where it's increasing and decreasing, this whole time I was on the way down, then I picked up, this whole branch is going down, this whole branch also down, so I'm decreasing the entire time. I'm never increasing. When I want to write the intervals, although I'd like to say everywhere, I need to say everywhere except -2 and +2. So I can either write everywhere except -2 and +2, or I can write it as 3 separate pieces, from -infinity to -2, from -2 to 2, and from 2 to infinity. As far as the end behavior goes, we need to look at the 2 ends. Both of the ends of the graph are leveling out at the horizontal asymptote, which was 0, so both of my y's approach 0 in my end behavior. To write the equation of the domain, I'm looking for all the values that x is not allowed to equal, which were from up above, my vertical asymptotes. X was not equal to -2 or 2, because those were my vertical asymptotes. When I go to do the range, this one's not as bad as the other one, because this one has 3 branches. So I need to look, is there anywhere that the y doesn't cover? If I choose this middle branch, the middle branch itself goes up and down forever, so it doesn't matter. I cross the horizontal asymptote, there's not any holes, y is an element of the reals, y can be anything for this graph. Let's go down to the next one. This is an example of a graph with a slant asymptote. Again, we're not going to worry about finding the slant asymptote, but I want you to see what one of these graphs look like. If I put this into my calculator, I'm going to have x squared minus 3x plus 2 on the top, divided by x plus 1 on the bottom. So I know this one's going to be slanted because the top has a bigger exponent than the bottom does. When I draw this, I only get a part of the graph if I'm in my INIT window. I know that this function should exist everywhere except where the bottom equals 0, so there has to be another piece over on the left side of the graph. I might try my view window standard. I can start to see that other piece down here on the bottom, or I could go to zoom out and hit enter, and then I can definitely see my 2 pieces. So you might have to zoom out to see a whole graph. Just be sure that you have everything that can fit on the graph paper. All right, so again, first thing I did was look for were there any factors that could reduce out. There aren't, so there's no holes. Then I said, where else is the bottom equal to 0? I only have one place the bottom is 0, and that's at x equals -1, so that's my vertical asymptote. To find the horizontal asymptote, I did the degree of the top over the bottom. So this one, the top was bigger, so I don't have a horizontal asymptote. This does not level out horizontally. It has a slant asymptote, and like I said, we're not going to find the equation of that. I can't tell if I have an x-intercept just by looking at my graph this way, but if I go to gsolve and I tell it to find the roots, I can see I have an x-intercept at 1, and that should make sense because if I plug 0 in for y into my original equation, doesn't matter what's on the bottom. All that matters is 0 on the top, because the first thing I'd do is I'd take this and I'd multiply it over to the 0. So looking at my equation, I have 2 zeros, x equals 1, and then I can hit the over button on my calculator, and also x equals 2. To find the y-intercept, I'm going to plug in 0 for x, or on my calculator, I can hit the y-intercept button, and my y-intercept is 2. So I would plot these points on my graph, and then connect them with my nice smooth points. For this graph to determine where I'm increasing, I can tell I'm increasing on this part, and then I start decreasing. I'm also increasing on this part over here on the end. So I've got to figure out where those turns were, where I changed from increasing to decreasing. This point down here was the maximum button. So on my calculator, I could hit gsolve max, and it will tell me the coordinates of those points. The other turning point was a minimum, so I can go to gsolve min, and it will tell me the coordinates of my minimum. For the end behavior, I have two ends. I have this end over here on the right. So as x is going to infinity, what's y doing? It's going up towards positive infinity, and that's my right end behavior. I also have this end down here. As x is going to negative infinity, y is going to negative infinity. My domain was just x is not equal to -1, because that's where the bottom was 0. And for my range, it was almost like the range of two parabolas. Y had to be less than or equal to the y value of the maximum, and y had to be greater than or equal to the y value of that minimum. Again, I know it's a lot, so we'll try some more practice with these in the next few days, and let me know what questions you have in class tomorrow.